I'm going to start by drawing a diagram here. This is the floor, and there's some chocolate, a bar of chocolate on the floor. And then 1 meter above, we have this device that attracts chocolate when it's turned on. Okay, this is 1 meters here. So what happens when it's turned on is that the chocolate's going to start rising, and it'll actually get faster and faster as it gets closer and closer because it's going to accelerate. The force that the device applies on the chocolate gets stronger and stronger because the force is described by this formula here. 1 over 35 r squared newtons for every percentage of cocoa. So r stands for the distance between the device and the chocolate bar. That distance starts at 1 meter, but as the chocolate bar rises, that distance decreases. And as that distance decreases, that's going to change the amount of force. Now, because the force is changing, then the acceleration is going to change. Newton's second law, acceleration is net force divided by mass. And since the acceleration changes, we cannot use the uniform acceleration formulas. We cannot use the uniform acceleration formulas. But that's okay. We can still use conservation of energy. So this will be point number 1. The chocolate bar starts at rest on the floor. It's going to rise until it gets to point number 2 here, which is described as being 10 centimeters lower than the device, 0.10 meters lower than the device. The question is, what is the speed at point number 2? We are told that the force from the device is a conservative force, so we can use conservation of mechanical energy. We are going to assume that air resistance is negligible. So what does conservation of mechanical energy look like when we have this make-believe new force? Well, it's going to look exactly the same, except we just have to add in this new term. So conservation of mechanical energy in general looks like this. The starting mechanical energy equals the final mechanical energy. However, for the U part, the potential part, we have to be careful. There's actually 2 different potential energies involved. There's one for gravitational potential energy, because this chocolate bar has mass. There is also one for this make-believe field. So there's a chocolate potential energy as well. Okay, so I'm going to rewrite it as gravitational plus chocolate potential energy. There's no spring, so I don't have to add the spring potential energy term in there. So that becomes my equation. It has 6 terms in it for conservation of mechanical energy. Though it's going to shrink a little bit because some of these terms are 0. For gravitational potential energy, we get to choose our reference height. So I'm going to choose the ground to be the reference height. And by doing that, my starting gravitational potential energy is 0 joules. Furthermore, this chocolate bar starts at rest. Since it starts at rest, the starting kinetic energy is also 0 joules. So my 6-term equation shrinks down to a 4-term equation. I'm going to calculate some of these energies. because I have the values for everything. So on the left side, the chocolate potential energy, we're given this formula for how to calculate the chocolate potential energy. So I'm just going to apply that formula to get the left side of this equation. Negative P. P stands for the percentage of the cocoa, which is a 70% chocolate bar. So it's 70. Divided by 35R. And on the right side of the equation, we have gravitational potential, which is mgh. The new chocolate potential energy, which is same formula, but it's at a different distance now, so it's going to be a different number. And then kinetic energy is half mv squared. I'm going to eventually solve for v. I'm going to plug in the numbers first here. So on the left side, negative 70 over 35 times 1 meter, because the chocolate bar starts 1 meter away from the device. mgh, the mass is 100 grams, so 0.100, 9.8 for g, and the height is actually 90 centimeters, 0.90 meters. Okay, that's the ending height. Since it's 10 centimeters below the device, it means it's only 90 centimeters high. The next chocolate potential energy is going to be negative 70 over 35 times 0.1. So R is the distance between the device and the chocolate, and we are looking at when it's only 10 centimeters away from the device at this point. And kinetic energy, I'm leaving it as half mv squared. I'm going to rearrange that for v later. Okay, so calculating these numbers out. On the left side, negative 70 divided by 35 divided by 1. That makes negative 2. Negative 2 joules there. On the right side, 0.1 times 9.8 times 0.9 is 0.882 joules of gravitational potential energy, minus 70 divided by 35 divided by 0.1. That is going to be 20 joules. Okay. I'm going to move all those joules to the left side of the equation. So negative 2 it's going to be minus 0.882 and then plus 20, giving me 17.118 joules. That's going to be how much kinetic energy this chocolate bar has, which equals to half mv squared. Now is when I can rearrange and solve for v. So the speed will be the square root of 2 times 17.118, just doing the algebra here, divided by the mass. The mass is 0.1. It's plus or minus, but the minus is inadmissible. Okay, so that is what I'll calculate out. Giving me, wow, that's really fast. It's 19 meters per second. So I hope that Sarah has really strong hands and can catch the chocolate bar when it's moving at 19 meters per second when it gets close to her device.